everybody can see my screen. You can hear my voice.
Yes, doctor.
Okay. So we are now in the final topics of chapter 5 regarding the phase transmission equation. So this topic is very important for your final exam, and I hope that you can understand my explanation. So if you don't understand, please ask me questions. Okay. So actually, last week we have learned until these equations. Okay, until here, until this slide. But I will refresh again from here, from the beginning of a phase transmission equation. So uh, before we proceed with the phase transmission equation, we need to understand the basic concept of the important parameters. Okay, so if you see from this slide, you can see the transmitter and also the receiver systems. Okay, so what you need to understand is the parameters involved in this system. For example, if you see here from the left, kita start dari kiri. So from the left here is the transmitter. Okay, from the left here is the transmitter, and then the power produced by the transmitter is what we call as PT. Okay, and then the power that produced by the transmitter is transferred to the antenna. Okay, transferred to the antenna, and in the process during this transferred power from transmitter to the antenna, it is transferred through through a cable. Okay, dia dihantar melalui transmission line cable, where it contains it produces losses. Okay, it produces losses, and the losses parameter is what we call as LT. So LT is a loss at the transmission line. Okay, so LT is the loss in the transmission line. Okay, dia losses disebabkan oleh boleh jadi disebabkan oleh attenuations, pelemahan signal. Boleh juga jadi disebabkan due to the any factors that disturbs the cable itself. Okay, but most of the time that we ask in the final exam, it is due to the attenuations, yang mana power yang dihantar daripada transmitter itu dia akan melemah disebabkan oleh distance. Okay, so this distance is about a few meters. Okay, it's about few meters, and if you see from the previous final exam, we give the parameters of LT in term of decibel per meter. Okay, biasanya kita berikan dalam dB per meter. That means the losses. So the losses is in term of dB per meter. Okay, and you need to know how long is the distance, is the long of the transmission line. Okay, so if the transmission line is about, for example, 5 meters, so you need to multiply it with the distance. Okay, so with the length. Okay, with the length, so that you get the losses in term of dB. Okay, so biasanya kalau you lihat saya cadangkan you lihat soalan-soalan yang lepas, yang mana losses ini diberikan dalam sebutan dB per meter. And when you want to find out how much is the losses in dB, so you need to multiply with the length of the transmission line, so you get the losses in terms of decibel. Okay, so normally we give the losses in terms of attenuation only. Okay, biasanya kita berikan dalam attenuation. Okay, so dia adalah pelemahan signal, also known as the losses in the transmission line. And later the power is transferred to the antenna, And the input power to the antenna is what we call as P in. Okay, power supplied to the antenna. And some very small amount of the input power is dissipated in terms of heat dalam haba. Okay, and most of the input power will be radiated by the antenna. So this is what we call as P radiation, the power that we use to radiate the electromagnetic wave. Okay, and and then we see that the transmitter antenna has a gain of GT. Okay, gain of uh, transmitter antenna. Okay, GT is the gain of transmitter antenna. And of course, when we transmit the electromagnetic waves, we're going to produce a EIRP. Remember, EIRP is the power multiplied with the gain. Okay, power multiplied with the gain. So in this case, P radiation multiplied with GT. Okay, kita darabkan dengan gain. So we get this. Yeah. So the wave travel from transmitter to the receiver. Form of spherical. So the waveform uh, shape is in spherical shape. Okay, dia dipancarkan dalam in theoretical it is in spherical shapes. Okay, and at the distance, a certain distance, you can say R or D, for example. So, for example, R, for example, distance meter away from the transmitter. So the signal received at the receiver. Okay, and at this distance, we can calculate the power density. Okay, power per unit area. Okay, so remember that power per unit area is also can be described as the strength of the uh, strength of the signal. Okay, dia juga menggambarkan kekuatan signal itu pada jarak tertentu. Okay, of course, the signal strength, the power density will be smaller uh, when the distance is higher. Apabila jarak itu semakin besar, maka power density semakin kecil. Okay, remember that PD is power, sorry, EIRP, power multiplied with the gain, divide with 4 pi r square. Okay, 4 pi r square is the area of spherical surface. Okay, and then the signal is received by the receiving antenna. The receiving antenna has a gain of GR. Okay, and then the power produced by the receiving antenna is what we call as a P out. Okay, and then the receiving transmission line has losses, what we call as the LR, losses in the receiving transmission line. Also, in the previous final exam, we gave the losses in the transmission line in terms of dB per meter. So it is in the form of attenuation. Okay. Normally, we give in the form of attenuations. And in the real world, the losses not only due to the attenuation, it can also due to the cable itself. Maybe the cable has a fault or somewhere else in the line where it can also produce losses. But for simplicity, we give the losses in terms of attenuations. So normally the LR and also the LT, we give a certain value in terms of dB per meter. Okay, that means attenuations in terms of dB per meter. So if you want to know the how much is the total losses or total attenuations in the transmission line, you need to multiply with the length of the transmission line in terms of meter. So you get in terms of dB. So LR in terms of dB. And then the power received by the receiver is what we call as the PR, received power by the receiver. Of course, power in terms of watt. Okay, power dalam sebutan watt. Okay, so this is the big picture of the transmission line parameters. Okay, so we're gonna look one by one. Okay, so here we start with the transmitter. Kita mulakan daripada transmitter. So EIRP is equal to input power to the antenna multiplied by the gain of the transmit antenna. Okay, so P in multiplied with the GT. Okay, so the power that we supplied to the antenna, we multiplied with the gain. So we get the EIRP. Remember, EIRP, the unit is in term of watt. Okay, dalam sebutan watt. And then when the transmitter antenna transmit the signal to the receiver, so you see that at distance D, okay, so here you use the D or you can use the R, it's up to you, no problem. So D or R, the distance, remember that the distance must be in terms of meter, okay. Normally we give you in terms of kilometer, but remember that you need to change the unit into standard unit, which is in terms of meter. So power multiplied with the gain, EIRP, divide with the surface area of a spherical. So 4 pi d square. So you get the power density. Remember, the unit is in terms of watt per meter square. Okay. And then what? How much is the output power from the receiving antenna, which is P out? Okay, P out is here. Okay, P out, power produced by the receiving antenna, okay, P out is equal to power density. Okay, remember this power density is the power density measured at the receiving antenna. Okay, power density yang diukur pada receiving antenna. Okay, of course ada dia punya jarak daripada transmitter kepada receiver. And then we multiplied with effective area of the antenna. Okay, effective area of the receiving antenna. In this case, it is referring to the effective area of the receiving antenna. So normally we give you in the previous exam we give the parabolic antenna where the surface of the parabolic antenna is circular shape. Okay, dia dalam bentuk bulat. So the area is a pi r square. Okay, the surface area of a circle is pi r square. But remember, this is a AE, effective area, so it is related to the antenna efficiency as well. So we're gonna see about AE later. Okay, we're gonna see AE in the next slide. So therefore here the equation is become P in multiplied with GT. So this is the EIRP divide with the power divide with the area of a spherical pi 4 pi d square and then multiplied with effective area of the receiving antenna. And then what? So we want to know how much is AE. So AE is the effective area of the receiving antenna. Okay. So effective area of the receiving antenna is equal to antenna efficiency multiplied with the actual area of the antenna. So this is what I mean by follow the circular shape, which is a pi r square. So r is the radius of antenna. Okay, ini adalah antenna regarding the antenna dimension. Okay, this area is the surface area of the antenna, luas permukaan antenna. So r here is the radius of the antenna, pi, and then r square multiplied with pi. So this is a circular shape. Dia dalam dia punya luas kawasan itu dalam bentuk bulatan. Luas kawasan antenna, permukaan antenna, the surface area. So the surface area, you see that the surface area, although it is a pi r square, but the effective area that contributes to the transmission and receiving is related related with the efficiency. Walaupun luasnya besar, tetapi kita perlu mengukur juga dia punya berdasarkan dia punya efficiency. That's why we multiply with the efficiency. So how much from the actual surface is contribute to the transmit and receive. Okay, so that's why we multiplied with efficiency. Remember, efficiency we give you in term of percentage, but if it is 80% of efficiency, don't put 80, you need to put 0.8 in the calculation multiplied with A. Okay, so common mistakes by the student, if we give the efficiency in term of percentage, they straight away put 80 in the calculation, which is wrong. Okay, so kalau diberikan efficiency contohnya 80%, so dalam pengiraan dia adalah 0.8 darabkan dengan area. Okay, so back to the GR. Okay, so GR is equal to 4 pi AE divided with lambda square. Okay, so this is okay, so this is FSL. 4 pi lambda square is related to free space loss. Okay, and then multiplied with antenna effective area of the antenna. Okay, so this is the equation for receiving gain. Okay, gain pada receiver. Okay, and if we rearrange the equation, kalau kita rearrange the equations, what we get is that AE is equal to GR lambda square over 4R. So this is if we rearrange the equations. So you see that this AE is also equal to this one. Okay, so that's why we can find AE. Okay, we can find AE using the area. Okay, using the area, the surface area of the antenna. Apabila kita memperoleh nilai effective area of the receiving antenna, it is also equal to GR multiplied with lambda square over 4 pi, where this equation is important for the phase equation. Okay, so kita apabila kita telah memperoleh persamaan apabila kita telah memperoleh value untuk AE, bermakna kita juga telah memperoleh jawapan untuk GR multiplied with lambda square over 4 pi. Okay, so AE, okay, AE of course this is area. Remember, area must be in term of meter square. Luas adalah dalam sebutan meter square. Okay, so the unit for AE is meter square because it is area, luas kawasan. Okay, and then so since we already find the value of AE, so then we can put inside the equation. Okay, so the previous equations is this one, P out, this one from the previous slide. We already get this parameter PD, but we don't know how much is AE. Okay, so if you see from this PD multiplied with AE, so now we get the full equations. PD multiplied with AE, so P in multiplied with GT, so this is EIRP divided with spherical area 4 pi d squares, and then multiplied with GR lambda square over 4 pi. Okay, so from here it becomes like this. So if we rearrange the equations, we will get these final equations for the P out. So this is what we call as the freeze transmission equation. Inilah yang dipanggil sebagai freeze transmission, okay, equation. Okay, so this is the freeze transmission equation. And for your information, in this freeze transmission equation, we only consider the losses due to the free space loss. Dalam case ini, in this case, we only consider the free space loss. Free space loss is the losses due to the distance, due to the attenuations. Okay, so the further away the distance from transmitter, the higher would be the free space. So free space loss is always in the equation. Dia sentiasa ada dalam equations. So this kind of loss is due to the attenuations, which is due to the distance from transmitter. Okay, dia sentiasa ada. Okay, dia memang kekal. So in this equation, we don't consider the LT and LR yet. Okay, kita belum mengambil kira nilai losses disebabkan oleh LT dan juga LR. Hanya disebabkan oleh FSL. Okay, so what is FSL? You can see from here, FSL is the sorry tidak jelaskan. So FSL is the losses due to the distance from the transmitter. So the term lambda over 4 pi d square is known as the free space propagation loss, also known as the free space loss. Okay, yang mana dia berkaitan dengan distance dan juga frequency actually. So the frequency effect, the lambda, remember that lambda is equal to C over F. Okay, so the frequency of the transmission affect the value of lambda, and this also contributes to the FSL. So it is sometimes more convenient to inverse that equation so that its decibel value would be positive value. Okay, so biasanya, kebiasaannya apabila kita menulis, kita akan inversekan dia. So it becomes a 4 pi d over lambda square. So it is actually, when we inverse this one, it becomes 4 pi d over lambda square. Why do we inverse like this? So that we get a positive decibel. So why do we need positive decibel? So that easy for us to do the calculation. Okay, so this is the reason why we do the inverse. In dB notation, positive number greater than 1 will give you positive value. For a value greater than 0 but less than 1, dB value is negative. So no dB value for negative number. So this is among the reason that why we inverse the equations. But we should know that this is contributes to the losses. So when we inverse, that means we need to divide the equations. Instead of multiplying, we need to divide. Apabila kita telah inverse, bermakna kita perlu bahagikan dia. So this is you don't confuse about this. Okay. When you multiply, it is lambda over 4 pi d square. When you do the inverse, that means you need to divide. So this is contributes to the losses. Okay, so jangan confuse. So don't be confused. It is the same because this here we multiplied. So when we inverse, that means we need to divide. Okay, so dia adalah kita susun dalam bentuk mathematics. But the main equation is this one. Okay. Okay. So jangan confuse. So from here we can find rewrite the equation in terms of decibel. Daripada sini barulah kita boleh buat dalam sebutan decibel like this. Okay, so you see that here P out is so here now we write all the equation in terms of decibel. Okay, sekarang kita tulis semuanya dalam sebutan decibel. Remember in decibel we do plus. We do the process of plus addition for a multiplication process in the actual value, and for the division in the actual value we do a subtraction process in the decibel. So you see that here P out is equal, so P out here, this one is in terms of dBW. Okay, here is in terms of dBW. Okay, so kalau dBW here is, this one must be in terms of dBW. So this one is dB, dB. Okay, so why this is minus? Because we divide this one. if you see from the previous equations, division in the actual values. So it contributes to the subtraction in the decibel process. Okay, kalau kita bahagi dia dalam kes ini, bermakna kita perlu buat proses tolak dalam decibel. Okay, so minus 20 log 4 pi d square, where this is FSL. So this is in terms of dB. Also dB. So this is a free space loss. Okay, so you see that everything that we minus here contributes to the losses. Okay, so here is all the losses. Okay, kalau ada losses yang lain, if we have another types of losses, then we need to put here after the FSL. So now we want to see what happens if we have another type of losses. Okay, before that, okay, before we move to the here, I want to explain about this one. Okay, regarding these equations, okay, in this equation, we consider only FSL as the losses. Okay, in this equation, okay, class, in this equation, there is no other losses other than the FSL. Dalam equation yang ini, tidak ada losses lain selain daripada space loss. In this equation, there's no LT, there's no LR. Tidak ada LT, tidak ada LR. Okay. So now we want to consider, what if we have the losses in the transmission line? Apa jadi kalau ada losses lain? Okay, selain daripada free space loss, iaitu losses in the transmission line and also in the receiving transmission line. What happened in the final equation? So let's look from here. Okay, so why suddenly use a PR? Because PR is the received power by the receiver after we consider all the losses, everything, all losses includes inside. Okay, so if you see from here, the PR, the power received by the receiver, is equal to PT times GT times GR. So this is the EIRP multiplied with GR, divide with the, so this is also divide with the FSL. Okay, divide with the FSL, and also LT multiplied with LR. Okay, so actually this I can put a long division like this. Okay, so this is a EIRP multiplied with GR, divide with FSL multiplied with other losses, LT and LR. Okay, so this is also phase transmission equation. Okay, ini masih lagi phase transmission equation, but in this case we consider other types of losses. Okay, remember class, in your syllabus we only consider this type of losses, but in the real world there are other types of losses, many losses over here actually. So dalam you punya syllabus, we only consider FSL, LT, and also LR as the losses. But remember, in the real world, there are other types of losses involved in the system. Okay, so that's why if you see from literature books, there's also another types of losses, another type of losses. So I put here multiplied with L, multiplied with another L, something. Other types of losses we need to consider inside the equations. But in your syllabus, it is enough just for the FSL and the LT and also LR. Itu sahaja. Ada 3 jenis losses. Okay, iaitu FSL, LT, and also LR. And then from this equation, we can derive the decibel equations. Okay, so therefore the received power by the receiver in decibel, so this is in dBW. So this is a dB gain gain, dB. And then here, you see that here, if you see minus here, that means all of this, okay, is a losses. Okay, ini semua adalah losses. All of these are the losses. Okay, so here is the FSL in dB, LT in dB, LR in dB. Okay, so that's why if, okay class, if you have other types of losses, that means we need to minus another L, minus L, minus L, minus L. So it depends. If you have other types of losses, we just need to put inside the equation minus losses, minus losses, minus losses. So all of this is the losses. So all of the minus here is the losses. Semua yang kita tolak itu, okay? The process of subtraction is that means that we minus the losses. Okay, kita tolakkan dengan semua jenis losses. Okay, so this is the equations that we want to use, okay, for the calculations. Okay, now let's look at the final example yang terakhir. Okay, so see in the previous final exam questions, this example is, we can consider the favorite question. Okay, ini adalah soalan favorite yang sering ditanya dalam final exam. Something like this, soalan yang seperti ini. Okay, so you see that example 14. A microwave link is to be set up between two cities which are 100 kilometer away. So that means you have here is the transmitter, here is the receiver. So class, I always suggest to the students, when you are given questions, I suggest you to draw on your own so that you can get the clear picture about the equation. Okay, saya selalu mencadangkan kepada pelajar, apabila diberi soalan, sila lukis apa yang kamu faham. Tak perlu cantik-cantik, no need to draw very nice, no need, just for you to understand the question. Okay, so you see that there are a microwave link means that we have transmitter and we have the receiver. So this normally to connect between two area or two cities, for example. So the distance here is 100 kilometer. So remember, if kilometer, you need to change to meter, 100,000 meter. So the distance between transmitter and receiver is 100,000 meter. And we use the frequency, the link operated at 3 gigahertz frequency using two parabolic horn feed antenna at both transmitter and receiver. Apa maksud dia? So that means the frequency is 3 gigahertz. Okay, we are using two parabolic horn feed antenna. So from here we know that both antenna are the same. Okay, dalam kes ini kita melihat kedua-dua antena adalah sama, exactly the same. Okay, dalam kes ini kedua-dua antena adalah antena yang sama, sebiji sama, exactly everything is the same. Okay, this transmit antenna, receiving antenna has the same parameter, so easy. Okay, but in the real world, you see that in the real world doesn't mean that we need to have a same antenna. Tidak semestinya kita perlu ada antena yang sama. Okay, dalam real world, in the real world, we can have a different kind of antennas, different transmit antenna, different receiving antenna. We can have that in the real world. But here, we use the same antenna, sama, exactly the same. Okay? So the parabolas are 1 meter in diameter. So you see that the diameter is 1 meter. That means the radius is 0.5 meter radius. So if it is a parabolic, okay, if it is a parabolic, that means the surface area is in the form of circle. Okay, dia punya luas permukaan adalah dalam bentuk bulat. Okay, parabola, you gambarkan bentuk parabola yang mana dia punya surface area itu adalah berbentuk bulat. Okay, so later when we want to calculate the surface area of the antenna, we use the equation of pi r square. Okay, the actual area of the antenna, parabolic antenna. Okay, and then what? And the efficiency is 80%. So both transmit and receiving antenna has the same efficiency, which is 80%. Okay, 80%. If the input signal is 20, okay, if the input signal is 20 watt, so you are given P in equal to 20 watt. So find the gain of the antennas. Find the gain of the antennas. So how to find the gain of the antennas? So you see that we can find the gain based on these equations. Okay, we can find the gain of the antenna based on these equations. Okay, okay, we can find based on GR equations, which is 4 pi AE lambda square. Kita boleh mencari nilai gain berdasarkan 4 pi AE over lambda square. So remember in these questions, okay, in these questions, GT equal to GR. Why? Because both antenna are the same. If both antenna are the same, that means they produce the same gain. Okay, kalau kedua-dua antenna itu sama, maka dia punya gain juga adalah sama. So in this case, we can find the GR, which is this one, 4 pi AE over lambda square. Okay, so 4 pi AE over lambda square. We can find lambda based on the frequency. We can find AE based on the area. Okay, so ni ada dia punya solution. So dia ada di sini. I thought tidak ada solution, so ada solution di sini. So you see that we can find the gain based on the GR parameters. So GR, which is a 4 pi AE over lambda square. So now we can find lambda. Lambda is equal to C over F. Frequency is given as 3 giga. Okay, so when you divide with the speed of light with the frequency, so you get the lambda is 0.1 meter panjang gelombang. Okay, panjang gelombang adalah 0.1 meter. Okay, after this we can find the effective area of the parabolic antenna. So the effective area is equal to antenna efficiency multiplied with the actual area of the antenna surface. Okay, so 0.8 antenna efficiency multiplied with the surface area of the parabolic antenna. So remember, surface area of the parabolic is in term of square. Okay, luasnya adalah pi r square. So we are given the r value, so we are given the diameter. So the question give us the diameter. So diameter needs to be divided into 2. Okay, so we are given diameter equal to 1 meter. So therefore R equal to 0.5 meter. Okay, so that's why antenna efficiency 80%. Okay, kita diberikan dalam soalan in the question give 80% of antenna efficiency multiplied with the area, actual area of the parabolic, actual area of the surface parabolic antenna, which is pi r square. So therefore we get the effective area is equal to 0.628 meter square. Meter square. Be careful. So class, remember, if you don't write the unit, I will not give you the marks for the final answer. Okay, remember, unit is important. Okay, I've asked you previously, if you still remember, saya pernah tanya apa beza antara 10 watt dan 10 You still remember my question in chapter 1. So you yourself already say that both are different. This one is in term of watt, this one is maybe this one is a value without a unit. So ada beza. Okay. Sama juga dengan ini. Kalau you letak 0.628, so what is this? It is power, it is what? Whatever. So we cannot just put a value. Remember, you must put the unit. If there's no unit, so never mind. Just put a value. Okay. Jangan tulis unitless. Jangan If the parameter has no unit, just put a numbers. No problem. Tulis nombor saja. Tak perlu tulis unitless. Sometimes it is agak lucu sedikit kalau kita tulis unitless. Unitless dalam nota cuma untuk menunjukkan dia tidak ada unit itu saja. Okay, and then okay, from here we can find GR. So GR, gain of the receiving antenna is 4 pi AE over lambda square. So 4 pi multiplied with the effective area of the antenna divide with lambda square 0.1 square. So we get 789.168. So no unit. This is the gain. Okay, and this is also equal to GT because both antenna are the same, exactly the same. Okay, dalam kes ini kedua-dua antenna adalah sama, so semua parameter adalah sama untuk antenna. Okay. Okay, the next question asks, how much is the EIRP? EIRP, remember that EIRP is equal to P in multiplied with GT. Okay, so P in multiplied with GT. Okay, so dalam kes ini kenapa dia buat GR sebab this is also GT okay, because GR and GT is the same, so it puts a GR over here, dia letakkan GR di sini. Okay, sebenarnya dia adalah GT so therefore you get 20 20 is given in the question, 20 watt. Okay, 20 is given in the question, 20 watt multiplied with GR. So GT and GR is the same. We got it from the previous question. Okay, 789.168. So we get here 15783.361 watt. This is the EIRP. Okay, and then what? The question asks how much is the power density at the receiver. So you see that from my picture here, you see that here. So okay. So how much is the power density at the receiving side? Okay, power density at the receiver. So power density is equal to EIRP, which is power multiplied with the gain, divide with 4 pi r square. 4 pi r square is the spherical area. Spherical is the surface area of a spherical. So 4 pi r square, remember the r here is regarding the distance from transmitter to the receiver. So this is actually 100,000. So please correct your notes. This is actually 100,000. Okay, not 100. Berhati-hati. So if you please use your calculator. Okay, cuba guna calculator. Ini sepatutnya 100,000 bukan 100. So you need to be careful. So I also will try using my calculator. So 15783.361 divide with 4 pi 4 pi
Sama jawapan.
okay, sama oh thank you. So saya tak perlu teruskan. Thank you very much. So senang sikit ada yang bantu I'm sorry. Sometimes I wrongly calculate the answer. So if you help me to correct me if I'm wrong, that's a good thing. Okay. So we get a power density is 1.256 times 10 power of minus 7 watt per meter square. So this is the power density at the receiver. Okay, pada receiving side. And then what? The question asks, how much is the free space loss, FSL? Okay, so normally when we ask about free space loss, even in the practical cases when we ask about FSL, normally we ask in terms of decibel. Okay, biasanya bila kita sebut pasal FSL, normally we sebut we pronounce in terms of decibel. Biasanya kita buat dalam decibel. Biasanya kebiasaan dalam real world, how much is the losses? Normally we say in terms of decibel. Okay, so in this case, you can use a 20 log 4 pi d over lambda. FSL is 20 log 4 pi d over lambda. So d here is the distance from transmitter to the receiver, which is 100 kilometer. Okay, 100 kilometer. So therefore here is 20 log 4 pi 100 kilometer, 100,000 meter divide with lambda panjang gelombang 0.1 meter. So we get here 141.984 dB decibel. Okay, so this is very easy. Okay, this is straightforward. This one. FSL, how much FSL? 20 log 4 pi d over lambda. Okay, you can remember this equation is also you can remember this one. Okay, and then what? The next question asks output power if the receive output power from the receive antenna, which is P out. Okay, so why do the question does not write in term of P out? Kenapa equation ini tidak menulis dalam sebutan P out? So if you ask me, it doesn't matter whether it is a PR or P out. Okay, why? Okay, why does it use a PR over here and not P out? Actually, you can put P out here. Okay, why? So the issue now is we don't have LT, we don't have LR. Okay, kita tidak ada LT dan kita tidak ada LR. So that means P out is equal to PR. Okay, so all of the power produced by the receiving antenna is received by the receiver. Semua power yang dihasilkan daripada receive antenna itu sampai kepada receiver. Okay, so don't be confused about this. So PR here is actually also P out kerana dia tidak ada losses yang lain. Okay, tidak ada LT, tidak ada LR. Okay, there's no LT, there's no LR. So that's why in this equation it puts a PR. So if you ask me, yes, you can put P out here. Okay, kamu boleh tulis dalam sebutan P out, no problem. Tidak ada masalah. Okay, so here is equal to PT. So remember here, this is must in dBW. This is also dBW. This is dB. This is dB. This is dB. Okay, so class, if here is dB, you can also put dBm, no problem. If this is dBm, that means this is also must be in term of dBm. Okay, if this is in term of dB micro, you can put dB micro. Here also must be dB micro. So dia kena sama. So power di sebelah kiri dengan power di sebelah kanan, on the left and the right side must be the same unit. Okay, because the rest is in term of decibel, so dia perlu sama. Okay, so here is dB, dB, dB. Okay, so we get a calculation in decibel. So P in decibel. Okay, ni pun satu lagi Okay, kelas. if you see from here, why does it put a PT over here? Previously we use a P in. Kalau you lihat di sini here we use a P in over here. Okay. So since now we use a PT, so now kita gunakan PT. Okay, so tak ada masalah. So dalam case ini, okay, I just want to give more explanation so that you don't confuse. So we use a PT over here because okay, so this is the complete equation actually. So PR equal to PT GT GR FSL. Okay, if okay class, if there's other losses, kalau ada losses yang lain selain daripada FSL, that means we need to minus another one, L in term of dB, minus again L dB, minus whatever losses we have. All the losses we put here. Okay, so this is the losses area. Okay, ini semua bahagian losses. Okay, so here suddenly dia buat P in. Kenapa dia buat P in? So dekat sini sepatutnya P in and PT is now becomes the same. Okay, because you see that power from the transmitter goes directly to the antenna, P in. There's no LT, there's no LP. There's no losses in the transmission line, so that's why digunakan P in. So ini sebenarnya merujuk kepada PT. Dalam case ini, in this example, PT is equal to P in. Why? Because there's no LT, tidak ada losses LT. Okay, dalam example ini, PT bersamaan dengan P in. Dalam example ini. Okay. And then what? GT, GR, FSL, we already get from the previous example. Okay. So we change all of this in decibel. So P in dalam decibel 13 dBW, GT in decibel, GT and GR is the same, sama. FSL we already got from the previous questions. So now we can put inside the phase transmission equations. So PR, okay, PR. So PR is, so you see the output power from the receiving antenna. So output power from the receiving antenna directly received by the receiver, because there's no LT, tidak ada LT, there's no LR. Okay. So that's why dia gunakan PR. So PR received by the antenna, which is also equal to P out in this case, in this example. So equal to PT. So PT in this example is actually equal to P in dalam example ini. Okay. So 13 dBW plus whatever gain we have. So we plus all the gains. Kalau ada gain yang lain, kita tambah juga di sini. If we have other types of gains that helps to strengthen the power, so we add all of the gains that we have. So in this example, in your syllabus, we only have two kind of gains, GT and GR. So we plus both of it. So GT and GR are the same. And then minus with the losses. In this case, we only have free space loss only. Hanya ada free space loss sebagai losses. And remember, class, if we have other losses, that means we need to here minus LT minus LR. So LT is 0, LR is 0 in this example. Okay, but if you see from the previous final exam questions, you need to calculate the LT and LR. So that's why in the final equation you need to include also the LT and LR. How much in term of decibel? Okay. Dalam previous final exam, kita perlu mengira dia punya LT berapa nilai LR. So ada tiga jenis losses. If you see from the previous final exam, there are three kind of losses. The first one is the FSL, the second one is the LT, and the third one is the LR. Okay. So in this, back to here, you see that 13 dBW plus 20.97 dB plus 28.97 dB minus FSL 141.984 dB. So we get the value negative 71.044 dB watt. Ini dia. So this is the final answer. So you see that here, this PR, okay, is also the P out from the receiving antenna because there's no LR, tidak ada LR. So kalau kita lihat gambar di sini gambar yang tadi tu So if I erase wait okay. So since we don't have LR, that means P out is directly transferred to the receiver. So there's no LR, that means P out is equal to PR. Itu yang saya nak katakan. Sebenarnya dia tidak sama. Okay, actually in the real scenario, it is not the same because we have the losses LR. Okay, but in this example, dia jadi sama dengan PR. Okay. So that's all for this. Sudah habis chapter 5. Do you have any question you want to ask about?
Betul.
Yeah, silakan.
Tadi example tu dia kata parabolic config kan?
Yeah.
So what are the other types of antenna and how do we determine the area for it?
Dia boleh jadi ada macam-macam lah. Tak semestinya parabolic antena. Biasanya kalau diberikan antena, dia akan tunjukkan macam mana bentuk surface-nya. Okay, dia akan tunjukkan macam mana bentuk surface, adakah bentuk circular atau square dan sebagainya. Okay, so dalam you punya syllabus, kita akan sentiasa berikan parabolic antena. Belum pernah kita beri antena jenis lain, tidak pernah. Okay, so maknanya untuk kamu punya syllabus, kita berpegang kepada parabolic antena sahaja. Yang mana dia punya luas kawasan adalah bentuk bulat.
Okay, thank you Dr.
Ada soalan lain nak tanya? Ya, ada kawan lain yang tak dapat masuk ke? Okay, ada soalan lain nak tanya? You have any question you want to ask?
Doktor,
Ya, silakan.
for LT dengan LR tu, kalau masa final nanti dia diberikan ataupun kita orang kena calculate sendiri.
Okay, biasanya LT and also LR, dia akan diberikan dalam sebutan dB per meter. Okay, normally we give the value in term of dB per meter. So how you want to find the value? You need to multiply with the length of the transmission line. Okay, caranya untuk kita memperoleh LT dan juga LR, kita perlu darabkan dengan dia punya panjang. Back to the picture, kembali kepada gambar raja. So I erase this one. So I erase this one. Okay. So this LT is depending on the length of the transmission line. Okay. Contoh for example, if the LT is given as for example 0.1 dB per meter, for example, contoh and the transmission line is given, the length of the transmission line is given as, for example, L is equal to 5 meter, for example. So this length is actually the length from transmitter to the transmit antenna. Contoh So therefore, the LT, LT is equal to 0.1 multiplied with 5. So we get 0.5 dB. Itu cara kita kira lah. That means we based on the given parameter. Okay. Biasanya, saya buat sebutan biasanya kita berikan dalam sebutan dB per meter. Okay. So depends on the question. If the question give you in term of decibel, so you can just use straight away in decibel. Okay. Kalau you lihat soalan-soalan yang lepas, dia berikan dalam dB per meter, yang mana kita perlu darabkan dengan dia punya panjang, baru kita dapat dalam sebutan decibel. Okay. Boleh
Okay, Doktor, boleh. Thank you.
Okay, so ada soalan lain nak tanya?
So doktor, untuk LT dengan LR punya equation kita nak calculate tu sama lah. Maksudnya kena darab dengan length of the
LT and LR. Okay, that's why we need to see the question. Kita perlu lihat soalan. Ada soalan yang lepas the previous final exam. Okay, kalau you lihat in the previous final exam, we give you only the LT, which is in term of dB per meter. I don't remember dB per meter. Okay, X dB per meter. And if you see in the previous final exam, we don't give you LR. Tidak ada LR, where you can assume it is equal to 0. Okay, so that means if you only been given LT, just use LT. LR is assumed as 0, no problem. Okay, so macam mana nak kira? So kita perlu lihat soalan. So what I'm saying is that from the previous experience, we give you the value in term of dB per meter. So mungkin saya tak tahu yang kali ni macam mana. Adakah diberikan dalam sebutan yang macam mana, saya tak tahulah. So biasanya tidak susah. Just we use we need to find the value in term of dB. That's it. Berapakah nilainya dalam decibel? So macam saya nyatakan tadi, dalam previous final exam, normally we give you LT only. Normally. So belum pernah ditanya tentang LR, if I'm not mistaken. Okay, but if given the LR, you can find the decibel, which is the decibel. Okay, normally we give dB per meter. Normally, so that's why you need to multiply with the length of the transmission line so that you get the value of dB. So itulah you kena cari dalam decibel. And then once you find the LT, LR, so you can put inside the equations. Put inside the equations, you can find the how much is the received power in dBW. Boleh? Okay.
boleh doktor. Untuk power losses memang unit dia dB sajalah. Memang tak boleh katakan dalam dBW dalam dB micro ataupun dB milli.
Okay. You mean dekat bahagian sini
Dekat losses.
Bahagian losses. Oh tak, losses we must put dB.
Okay.
Sebab kenapa dia macam ni sebab dia adalah satu value without a unit. So that's why when we convert into decibel, it becomes dB. Okay. Seperti yang saya nyatakan tadi, kalau you lihat ni So what I mean here is that if you see, if depends on the PR and PT. So the power, when we mention about the power, okay, power dia boleh jadi dBW, dBm, dB micro. Okay, so if on the left side PR here is dBW, that means on the right side must also be dBW for the power only. Okay, supaya dia kena sama. Okay, saya beritahu dia punya cara yang mudah adalah kita perlu faham bahawa dia perlu sama. Kalau PR dBW, that means the PT also in dBW. If PR is in dBm, that means the PT is dBm, and so on.
Doktor, saya nak tanya,
Okay.
once kalau soalan diberi power tu in dB, perlu tak kita kena tukar dia jadi dBW ataupun dBm atau dB micro?
Okay, power dia tidak dalam
Diberi
dB.
dia diberi dalam dB.
Power dalam dBW.
No. The question given, the power is dB, so kita perlu tukar tak jadi dia dBW? Convert guna formula daripada chapter 1 tu.
Dia gini, power ya. Power dia bukan dB power dia adalah dBW for power. dBW, dB milli, dB micro, is for power.
Maksudnya dia tak akan lari daripada unit ni lah.
Unit mana?
Betul tak?
Kalau
Unit
unit watt.
dBW. Ya.
Kalau diberi dalam unit watt, it depends. Kalau you nak gunakan Friis equations, that means you need to convert either of this dBW, dBm or dB micro. So that's why you need to look at the question. The question asks in terms of what? dBm, dBw or dB micro. Normally, if you see from the previous final exam, it asks in the form of dBw. It means you need to convert into decibels. So 10 log of power, you get dBw. 10 log of power divided with 1 milli, you get dBm. 10 log of power divided with 1 micro, you get dB micro.
Baik, Doktor. Terima kasih.
Tak ada? Kalau tak ada, saya nak pergi ke chapter 4 sekejap. Ada soalan tak?
Doktor,
Yeah.
what's the topic for the final exam? The important topic.
The important topic for the final exam.
Yes.
Final exam, we have 5 questions. One question for each chapter. Chapter 3, since chapter 3 we already asked about AM, so now we will ask about angle modulations for chapter 3. Yang lain semua, chapter 4 is about PCM. Chapter 4. Chapter 3 is about angle modulation. Chapter 2 about noise. The noise, okay, the noise calculations. And then chapter 1, standard, we have the theoretical and also the calculation about dBW and so on.
So, Doctor, can you repeat again the chapter 4?
Chapter 4, pulse code modulation, PCM. If you see from my video, I gave you 2 videos for chapter 4. The first video, I think the first video is the one that will come out in the exam. Okay, up to PCM, which is pulse code modulation is before the digital transmission. Okay, dia adalah topik sebelum digital transmission. Dia ASK, FSK, PSK tak masuk. Okay. Ada soalan chapter 5 ni? Kalau tak ada, saya nak pergi sekejap.
One more, Doctor.
Silakan.
Chapter 5, the whole topic, right?
Chapter 5, the whole topic, is it? Topic for today and also a bit question about transmission line. Tidak ada soalan yang spesifik antena, tidak ada.
Okay.
Okay.
Alright. Thank you, Doctor.
Okay, so kalau if you don't have question about chapter 5, I want to show you about chapter 4, about this one. Okay, so chapter 5 dah selesai. So I just want to show about this because in my previous video, I didn't show about this topic. I didn't explain clearly about this topic. Okay, saya tidak jelaskan dengan lebih panjang lebar berkenaan dengan topik ini. So, uh, so this is a folded binary. Okay, this is a folded binary. Okay, if you see from here, I'm not sure whether you dah belajar chapter 4, you dah belajar sendiri atau belum let's assume you belum belajar lagi so tak apa. Okay. So about folded binary, I want to explain about this and this because this also related to this one. Okay. So if you see from here, okay. So this in this example, this is about the process of PCM, pulse code modulation. Yeah. Okay.
Doktor,
Yeah.
can you back to the example 14, chapter 5? Sorry.
Okay.
I just want to ask the R.
Which one?
Question C. Why the R which is 100K? Is it for radius or what?
This is
Mi-
D actually.
Meter kan? Yang
Yeah,
yang doktor tadi kata kena
100,000.
convert meter.
100,000. So this is actually
100,000.
this is actually 100 kilo. The question gave 100 kilometers. So this is actually 100,000 meter.
100,000, yeah.
Okay.
Okay.
Doctor, just wondering why is it I know it's 100,000 meter, but why are we using that instead of 0.5? Like, I don't get that part.
0.5. Which one?
You know, like they gave the diameter of the whole thing was 1 meter, right?
Yeah,
So
this one.
the radius is 0.5. And like, why don't we use 0.5 instead?
Oh, you mean for this question
For
or
C.
for
Still
C?
for C. Yeah.
Okay. So okay. This is actually referring to the distance from transmitter to the receiver. It is not related to the dimension of the antenna. Okay, dia tidak ada kaitan dengan dimension antenna because this is a power density. Power density is how to let me draw something here. So this is the transmitter, this is the receiver. So you see that when the transmitter transmit the signal, it is in spherical shape like this. So the power density is the power that we measure at the point of the receiving side. Okay, so PD. So power density is equal to power, so EIRP divide with the surface area of a spherical, which is 4 pi r square. So this area is actually the luas kawasan gelombang dia punya pancaran gelombang itu dipancarkan dalam bentuk spherical. Okay, the wave when it travel from transmitter to the receiver, dia punya gelombang itu in theoretical bentuknya adalah spherical, bentuk sfera. And sehinggalah dia sampai pada receiving point, kita nak mengira berapakah kekuatan signal pada receiving side. So we want when we want to calculate the power density, it is EIRP divide with 4 pi r square. So this 4 pi r square is actually the surface area of a spherical. So dia sebenarnya kalau kita buat dia sebenarnya macam ni bentuk dia. Theoretically Okay, so mungkin you confuse yang ini sebenarnya bukan merujuk kepada antenna dimension, dia merujuk kepada distance daripada transmitter kepada receiver. So this R is actually not the dimension of the antenna, it is the distance from transmit antenna to the receiving antenna, which is 100 km. Jarak dia jauh. So this R is actually a 100,000 meter. So the one that you asked is actually referring to this one, 0.5. So the question that you asked is actually referring to this thing. So this is actually regarding the dimension of the antenna. Okay, because we calculate the AE. AE is the effective area of the antenna itself. Dia merujuk kepada luas kawasan permukaan antena. yang mana diberikan diameter antena 1 meter. So kita perlu menggunakan pi r squared. So remember in this chapter in your syllabus we only use parabolic antenna where the surface of parabolic antenna adalah berbentuk bulat. Permukaan parabolic antenna dia berbentuk bulatan. So that's why the actual area of the parabolic antenna is pi r square. Okay, ni luas kawasan bulat adalah pi r square. So the question that you ask is actually referring to this thing actually. Okay, permukaan. Yang tadi tu bukan permukaan antena, dia adalah luas permukaan sfera, iaitu bentuk gelombang itu yang dipancarkan daripada transmitter. That's it.
Okay, thank you. Yeah, I get it. I got confused with the power density just now, so like, yeah, I get it now with the drawings after you draw. So
Yeah. So
thank
it is actually like this. So itu sebab saya buat bulat. So it is actually the further away the distance from the transmitter, that means the density, the power density will become smaller. Dia akan kekuatan signal itu menjadi semakin lemah apabila jarak daripada transmitter kepada receiver itu semakin jauh. So that's why it is depending on the distance, d square. So kalau lagi jauh, maknanya dia punya density dia semakin kecil. And theoretically, we want the power density to be as large as possible. Kita ingin power density sebesar yang mungkin. Okay, secara teori. Boleh
Okay,
Yeah.
Doktor.
Thank you, Doctor.
Okay, ada lagi nak
Thank
tanya?
you. Nope, tak ada.
Okay, kalau tak ada saya nak pergi ke chapter 4. Okay, kalau nak tanya lagi boleh, no problem. Tak ada masalah. So bila ada banyak soalan, silakan ya.
So formula untuk power loss density tu memang pakai D, diameter, bukan radius.
Power density.
Untuk C tu tadi doktor tukar RD.
Okay.
Dia memang pakai D, bukan R.
Okay, dia gini macam ni Dia power density is equal to EIRP divided by 4 pi R square or 4 pi D square. Why I put D? Okay, kenapa saya tulis D? Sebabnya ini so kita kembali kepada persamaan yang sebelum ini So I just want to wait. Mana tadi Sini pun boleh lah sekejap Kenapa saya buat D? Kerana ini okay, why I write D? Because this is in the previous slides it used D, and then in the next slide dia gunakan R. So jangan confuse yang mana even although this is D or R, doesn't matter. Okay, doesn't matter D or R. The thing that you must understand is that the D or R is actually the distance from transmitter kepada receiver. So dalam you punya slides ini, dia tukar-tukar. Kadang-kadang dia letak D, kadang-kadang dia letak R. So I don't want you to confuse. You can put D or R, doesn't matter. The thing is that you need to understand that this parameter referring to the distance from transmitter to the receiver. And if you see from the previous slides, kalau kita pergi kepada slide yang sebelum-sebelum ini, ini dia dia guna D The previous slides used D, suddenly dia buat R. So that's why I don't want you to confuse. Lain kali saya kena tukar lah nota ni supaya dia guna seragam D supaya tak confuse. Ini pun dia letak R Sometimes it use R, sometimes it use D. So don't be confused. R or D is actually referring to the distance from transmitter to the receiver. Boleh
Thank you, Doctor.
Okay. So kalau tak ada soalan, saya nak pergi kepada chapter 4. Chapter 4, I want to explain more about this because in my video, this is from my first video on chapter 4. Okay, chapter 4, I provide 2 videos. I don't know whether you already seen the video or not. but this is from the first video, okay, about PCM. So remember, in the digital we have three process, formatting process. The first one is sampling, and then we go to quantization, and then go to the encoding process. Okay, encoding process. So sampling process is a process of changing from continuous time signal into discrete time signal. And then quantization is the process of rounded up the sampling value to the nearest quantized level. And then encoding is the process to assign a code word to the sampling, to the sample, to the quantization level. Okay, encoding adalah proses untuk assign code. Okay, we assign a code for each sample. Okay, so encoding is the process of assigning a code for each of the sample. So this is produce PCM, pulse code modulation code word. Okay, so to understand this, you need to watch my video sebab kita tak kelas sebelum ini cuti, so saya gantikan dengan video. So you need to watch the video first so that you know the three processes: sampling, quantization, and encoding. So this is about encoding process. Okay, so if you see, here is the 3-bit folded binary code. Okay, 3-bit folded binary code where the range is from 3.5 volt until negative 3.5 volt. So the distance is 7 volt, 3.5 until minus 3.5. And these codes use 3 bit. Dia menggunakan 3 bit. Sorry. It uses a 3 bit. 3 bits means that we're going to have the number of quantization level is 2 power of 3, which is 8. We're gonna have 8 codes from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Sorry, this is 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So we have 8 codes. Okay, so now the issue is how we want to assign the codes. So that's why I want to give more explanation about this. And the term of folded binary in this case, okay, folded binary means that since we have two polarities, positive and negative voltage, that's mean when we do the folded binary, that means we assign the codes equally for positive polarity and also the negative polarity. Okay, so let me draw this one. So this is actually slide number 36, if I'm not mistaken. Okay, kalau tak silap saya, slide number 36. Okay, slide number 36. So later you can refer to slide number 36 and 37. So this is also related to this. So you see that here, it is from 3.5 volt. Okay, it is from 3.5 volt until negative 3.5 volt. And we have the 3 bits code. So and here is okay, the x-axis is referring to the time. Okay, paksi x merujuk kepada masa. And here we have the graph. We have the graph. Kita ada graph yang ini. So this is the graph, and we take the sample. Each of this is a sample. We take sample. So this is actually referring to the sampling time. Okay, sampling time 3ts, 4ts, 5ts, sampling time. Okay, so sampling time. So how to know the ts is equal to 1 over fs, sampling frequency. So we get the sampling time in terms of second. Okay, so I want to further elaborate about this. Saya nak terangkan lebih lanjut berkenaan dengan slide number 36 and 37. Okay, and so let me explain. Let me have a drawing here. Okay, saya perlu lukis sedikit supaya pelajar lebih faham ya. So now, okay, but when you want to understand this, you need to watch my video first. You need to understand the process of sampling, quantization, and encoding. Once you dah tahu, barulah you boleh faham apa yang saya explain pada hari ini. So I want to further elaborate about that slides 36 and 37 because this is related to the folded binary. Okay, this is related to the folded binary. Okay, so now it is given that the range of quantization, okay, the quantization range is from 3.5 until minus 3.5. Okay, and here we have a 0. Here is actually the time. Okay, so now if you see from here, we are using 3 bit. Okay, dia menggunakan 3 bit. Okay, which is n equal to 3. So therefore the quantization level that we have is 2 power of 3, which is sorry, padam ni. 2 power of n, 2 power of n, which is here is 2 power of 3. So this is 8. So we have 8 levels. Okay, so 8 levels is from here between 3.5 to negative 3.5. We gonna have 8 levels. Okay, akan ada 8 so 1 2 3 4 5 6 7 8. Akan ada 8 levels excluding 0. Okay, so in the folded binary it is excluding the 0. So you see that quantization level I'm gonna have 8 levels, and the quantization range is from 3.5 to minus 3.5. So quantization range, okay, quantization range so this is regarding the peak to peak voltage. So this is regarding the peak to peak voltage. So this is actually 3.5 volt minus 3.5 volt. Okay, so the range is 7 volt. Okay, dia punya jarak daripada yang paling atas kepada yang paling bawah adalah 7 volt. Okay, and then we can find the resolution. Resolution is the step size. Okay, so tadi 7 volt is from here. So I just want to show you that 7 volt is this one, 7 volt. And then we want to find the resolution. Resolution is the step size. Berapakah dia punya jarak setiap tangga ini, berapa jaraknya? Okay, so the resolution, resolution or the step size, jarak tinggi anak tangga tu okay, jarak senggat tu adalah bersamaan dengan is equal to V peak to peak divide with dynamic range. So this is equal to, okay, this is equal to 7. Okay, sorry. This is equal to V peak to peak divide with 2 power of n minus 1. So the number of level minus 1. Why do we need to minus 1? Because we are excluding the 0. Okay, we are excluding the 0 volt from the calculation because 0 volt is considered as a neutral level. Dia tidak dikira dalam quantization level. Okay, walaupun quantization level ada 8, but the dynamic range is 2 power of n minus 1, 1 less than the quantization level because we are excluding the 0 volt, the x-axis. Faksi x tidak dikira. So dalam kes ini, so we get here is 7 divide with 2 power of n. So 2 power of 3 minus 1. So we get 7. So 7 divide with 7. So we get here is 1 volt. So how much is 1 volt? So 1 volt here means that the distance here is 1 volt. Okay. The distance here is, sorry, saya buat. So the distance here is 1 volt, 1 volt, 1 volt. Okay. Here is 1 volt, 1 volt. Here is 1 volt, 1 volt. Jarak dia antara 1 volt. So saya ada 7 kali 1 volt. 1, 2, 3, 4, 5, 6, 7. Okay. So I want to draw here, which is this one is minus 2.5, minus 2.5, minus 1.5, minus 0.5. Here is 0.5, 1.5, 2.5, and finally 3.5. So the distance here is 1 volt. Resolution is 1 volt. Jarak antara senggat itu adalah 1 volt. So in this case, we are using what you call uniform quantization, yang mana setiap jarak itu adalah sama. Okay. So when we can also draw a table. Kita boleh buat satu table untuk menggambarkan slide number 36 and 37. Okay. So I want to draw a table so that you can have more understanding about how do we assign codes for each of this level. Macam mana kita nak assign codes untuk setiap level ini? Okay. So in order to do that, we can draw a table. Okay, kita buat satu table. Yang mana di sini you boleh letak so here I can write here is a decimal. Decimal point. Decimal point. Here is PCM code word. Here, since we are using 3 bit, so this is a 3-bit PCM folded by code word. Code word. Ini tak nampak saya buat balik sekejap. And then we're gonna have a range of voltage. Range of voltage. Okay, so tadi kita kira kita ada 8 level. Remember that we have 8 level. If you still remember, when we do the calculation here, we get 8 levels. Mana tadi? Ni we get 8 levels of quantization. Kita ada 8 level quantizations. That means we're gonna have 8 over here. We're gonna have 8 rows. Kita akan ada 8 row. 1, 2, 3, 4, 5, 6. Okay. So we have 8 levels. Saya kecilkan sikit. So 8 levels, that means we're gonna have levels from 0, 1, 2, 3, 4, 5, 6, 7. So saya akan ada 7 level. Okay. So what is this level actually? So this level is representing this one actually. From minus 3.5 until 3.5 volt. So this is actually voltage. So I put voltage V. So here you see that since I use a 3-bit, so that means I'm gonna have 8 levels. Ada 8 quantization levels. So this is not a normal level, this is a quantization levels. Okay, so that means the PCM code word range from 000. So say about here 000. Remember we are using 3-bit, and then 001, 010, 011, 100, 101, 110, 111. Okay. How about the range of voltage? So range of voltage here is, remember this is from the below, the lowest level. Okay, so the way we assign the code word, normally we assign from the lowest level to be 0, and the highest level would be the highest number. So from 0 until 7 in terms of decimal. Okay, so kalau you lihat di sini, okay, the way we assign code. So in the standard, there are many ways to assign the codes. Dalam real world, ada beberapa cara untuk assign the code word. Okay, but I'm going to show you the simple one is that we assign the codes starting from 0 for the lowest level. Cara yang mudah untuk kita assign codes adalah dengan memberikan nilai kod yang kecil, iaitu starting from 0 for the lowest level of voltage, and we give the codes 111 for the highest voltage. So normally we start from 0, we start from the lowest voltage. Kita mulakan daripada voltage yang paling rendah. Dalam kes ini adalah negative 3.5 volt. Okay, so you see that's why I gonna start from here. You see that the range of voltage here from negative 3.5 to, so this is dalam volt, so saya tak perlu letak V. So kita tahu bahawa ini adalah dalam sebutan voltage. So from 3.5 to minus 2.5. Okay, minus 3.5 to minus 2.5. And remember that the range is 1 volt. Jaraknya adalah 1 volt, which is the resolution. This one. From minus 3.5 until minus 2.5. Okay. And then minus 2.5 and to minus 1.5. Ini saya padam sikit aja. Okay, daripada 2.5 volt to 1.5 volt. So you see that the resolution also 1 volt. Okay, and then from minus 1.5 volt until 0.5 volt. Minus 0.5 volt. So this is also, the distance is 1 volt. Okay, and then what? From minus 0.5, so this is the tricky part. So this is the tricky part where we reach the x-axis. So dalam case ini, kita ada zero, what we call as the neutral axis, the neutral level, the x-axis, where the x-axis, in this case, we divide into 2 parts, positive and negative parts. Okay, pada x-axis ini sebenarnya dia seolah-olah ada positive and negative sides. Okay, yang mana kalau kita lihat, dia sebenarnya actually this is minus 0.5 to 0 volt, 0.0. So 0.0 until 0.5. So this distance is 1 volt. So you see that the binary is folded at the 0 level. Dia seolah-olah kita macam lipat dia di bahagian tengah tu. So if I go back to the slide, I just want to show you this chapter 4. This one, right? Okay. Okay. So if you see from these slides, okay, from these slides, you see that the 0 volt is divided into positive and negative 0. So dia seolah-olah macam dia bahagi dua. So this part, you see this part, it divides into two, where here is the X center here. So you see that this is around, this is the folded binary. Okay, so why do we do this? Because this gonna be the changes of polarity from positive to negative. Berlakunya perubahan polarity daripada positif ke negatif or negative to positive. Okay, so in this case, it divides into two parts for the zero axis. Okay, dibahagikan kepada dua dalam kes ini. So nanti you akan lihat bahawa, the amount of codes that we assign to the level is actually the same. Kita assign level itu sama antara positive and negative polarity. You're going to see later that we assign the same numbers of codes for positive and negative sides. Remember, we have 8 codes. We use 3 bits and we have 8 levels. That means I need to have 4 levels for the positive sides and 4 levels for the negative sides, so that it looks like a folded. Kalau kita lipat dia sama, seolah-olah macam kalau you lipat kertas, lipat kepada dua, dia akan ada simetri antara atas dan bawah. So I go back to this to the explanation. Okay. So from here, so this is where we do the folded binary over here, folded at 0, at 0 volt. Okay, and then from here 0.5 to 1.5 volt, and then 1.5 volt to 2.5 volt, and then 2.5 volt until 3.5. So kalau kita lihat, okay, class, if you see from here, wait, if you see from here, okay, so I have 4 levels on the positive sides. I have 4 levels on the negative sides. Okay, saya ada 4 level untuk setiap polarity, positive and negative sides. Okay, I divide the quantization levels. Quantization level saya divide kepada dua bahagian, iaitu positif dan negatif, yang mana dia seolah-olah simetri. So in this case, since I have 8 levels, I use 3 bit. Saya gunakan 3 bit. That means 2 power of 3 are going to have 8 levels of quantizations. So I divide, if I want to make it a folded binary, that means the positive, the number of levels is equal for the positive and negative sides. Okay, and then what? So you see that, okay, ni so daripada sini, okay, from here, so now we can what I see that we can make a line like this. Kita boleh lukis seperti ini. So So here we can have if we have a signal, kalau kita ada sample signal, for example, we have a signal something like this. If you have signals, let's do green color. Katalah we have a signal like this. If we have signal like this, and we want to see the sample value. So you see that here I'm gonna have here is for example contoh so how to find the sampling time TS. So TS is equal to 1 over Fs. Okay, what is Fs? Fs is the sampling frequency. If my sampling frequency, contoh example, if Fs is equal to 10,000 hertz, 10 kilohertz. So therefore, my sampling time is 1 over 10,000, which is equal to, ni berapa? 1 bahagikan dengan 10K. So you akan dapat 1 kali 10 kuasa 4 or 0.1
0.1 milli.
millisecond. Okay. So in this case, you're gonna see that let's do red color. Let's do red color. So for example, contoh saya buat senggat 0.1, 0.1. Here is 0.2. Here is 0.3. For example, 0.4, 0.5 dan seterusnya. So if I want to find the sample value, so you see that the sample value here is, for example, here is 2 volt, for example. Contoh. Here is, for example, here katalah di sini adalah 2.2, for example, 2.2 volt. Okay. The sample value is 2.2 volt. So when I want to do the quantization, I need to round it up to the nearest quantization level. So apabila saya buat quantization, saya perlu bundarkan kepada nilai quantization level yang terdekat. Dalam kes ini, dia adalah merujuk, dia akan pergi kepada 2.5 volt. Okay, when I do quantization, I will round it up the value to the nearest quantization level, which is 2.5 volt. So 2.5 volt, okay. So 2.5 volt is okay, it is between a 110 and also 111. Ini kalau saya bagi contoh ni agak confuse sedikit So okay, sorry. Sekejap Okay. So dalam kes ini, okay. Sekejap Okay. Range of ini sebenarnya range of sample range of sample voltage. Okay. Saya tadi patutnya tulis range of sample voltage. So sekiranya sample voltage itu jatuh di antara range ini, berapakah kodnya? Okay. So kita tak nak bundarkan dia kepada directly 0.25 So ini mungkin saya kena padam lah untuk elakkan confuse Saya nak padam dulu sorry elakkan confuse. So saya padam yang ini. Okay. So let's say my sample value is 2.2 macam saya buat tadi 2.2 volt. For example, sample value. Okay. Saya ambil sampel pada 0.1 milliseconds so this is actually milliseconds. So at 0.1 millisecond, for example, I get the sample 2.2 volt. So 2.2 volt, okay, 2.2 volt is in here. You see that 2.2 volt berada antara 1.5 until 2.5. That means the code word for this one, okay, the code word for this one is 110. kerana 2.2 volt berada pada range yang ini. Okay, so this is actually I can give this one, the code word is 110. Okay, 110. Okay, 110. And then here, for example, here is 3.5 katalah ini 3.5 volt. 3.5 volt is, the code is 111. 111. And then here katalah at 0.3 millisecond, the value is here is 0.1, for example, 0.1 volt. Contoh example. So 0.1 volt is, the code is here 100. Contoh 100. So the code is 100. Bukan, not 100, 100, sorry different 100 and 100 is different So the code is, this is in binary So class, the code here is in binary. Dia bukan dalam decimal. That means the way we pronounce it is 100. Okay. And then here, for example, 0.4 millisecond, the sample is, for example, here is negative 2.4. Contoh negative 2.4. So negative 2.4 is here, somewhere here, this one So the code is 001. Kodenya adalah 001. And then here is, if you see from here, here for example 3.3, katalah di sini adalah 3.3 volt. So minus 3.3 So the code is here 000. Okay, 000. So now I can rewrite here. I can rewrite in terms of PCM code. So now the PCM code is, for each sample, so pada setiap sampel tadi yang saya ambil daripada 0.1, 0.2, 0.3, 0.4 dan 0.5. So you see that the code word becomes like this, 110 for the first one. And then the second one is 111. 111. So the here is 111. Alamak, saya punya freeze pula. Pelajar semua boleh dengar suara saya?
Dengar ke?
Boleh.
Saya kalau guna whiteboard ni dia jadi freeze sekejap. Semua boleh dengar suara saya?
Boleh ke?
Okay, kejap sorry. Saya punya ni freeze. Kejap. So, okay. Hopefully now is okay. Okay. So, I continue again Saya sambung tadi. Okay, kejap So, the first code that I get is 110 for the first sample. Okay. Second sample, I take the sample at 0.2 millisecond. And the code that I gave is 111. 111. The third sample I take at 0.3 millisecond. So the code here is 100. We already found this one. The code is 100. Okay. And then at fourth sample at 0.4, I take the sample and I already found the code is 001. The fifth sample here at negative 3.3 volt, the code is 000. So this is what we call as a PCM code word. Okay, where you see that here is the first sample, second sample, third sample, fourth sample, and fifth sample. Okay, saya ada 5 sampel dalam case ini. So when I write the code word is 110, 111, 100, 001, 000. So how do I find this? That means I need to make a table like this so that I can determine the codes for each of the sample voltage. Okay, kadang-kadang nilai sampel itu dia jatuh di antara tengah-tengah ini. So where do you want to go? Is it 2.5 or negative 1.5? So we need to see based on the table like this. Okay, daripada table ini barulah kita boleh tentukan berapakah nilai kod yang sepatutnya untuk setiap sampel. Okay, so from here maybe I can go back to the slide. Okay, I can go back to the slide, this one. So you see that from here, so this is another example. Okay, you see that here is, so you see that here the sample value is 1.3. Okay, so 1.3, the nearest is 1.5, and given the code number is number 5101. So this is the code word is 101, 111, 110, 11, 100, 011, and so on. So you see that here, ni tak boleh nak padam lagi . Oh, boleh padam sekejap . Okay, so you see that here, this is the first sample, second sample, third sample, until 7 sample. Okay, kalau dilihat di sini, here, so ni yang paling dekat, kalau ditunjuk di sini, sample is 1.3 volt. Okay, and the nearest is 1.5 volt, so dia bundarkan kepada 1.5, so the code is 101. So ini sama konsep macam yang saya terangkan tadi, same concept as I explained to you previously. Okay, so here also give the codes. The codes is given from 3 bit menggunakan 8 level. So we have 3 bits from range from 0 until 7. We have 8 levels. And each levels, the step size or the resolution is equal to 1 volt. Kalau kita lihat daripada minus 3.5 until 3.5 until minus 3.5, the resolution is 1 volt. 1 volt. Semua ni 1 volt. Dia punya distance, resolution. Resolutionnya adalah 1 volt. Okay. And from here, between negative 3.5 to 2.5, so you can, if the sample value between this range, okay, so kita boleh assign berapakah dia punya codes, macam tadi yang saya buat. So you need to do the table first so that you can determine what is the suitable code for each of the sample. Okay, so apa saya selalu sebut sample apa benda tu. So saya padam je. Yeah. So this is the signal. So this is the signal. Okay, this is the signal. And when we want to do the sampling, we take sample. For every sampling time, kita akan ambil sample. Setiap sample time, kita ambil sample. Okay. So dalam case ini, saya ada 7 sampel. So this is the sampling process. And then, after I do the sampling, I round it up to the nearest quantization level and I assign a code word for each of the sample. Saya ambil sampel dan saya bundarkan dia kepada quantization level yang terdekat, kemudian saya assign dia punya code word. So I have 7 samples in this example and I assign a specific code word for each of the sample based on the quantization level. So the code word, the process of assigning code word is depending on the levels. Okay, proses untuk memberikan nilai code word itu bergantung kepada quantization level. Macam yang saya buat tadi, saya buat tables. So apabila sample value itu jatuh di antara range tertentu, kita boleh tentukan berapakah dia punya code word. Okay, and in this example, you see that here the code word is 101 for the first sample, 111, second sample 110. Ni yang bawah ni dia ada tentukan di bawah ni 100. Ini ada ditentukan di sini. 011, 01, 001, 000. Macam mana dia tentukan nilai code word ini adalah berdasarkan nilai berdasarkan table yang seperti saya buat tadi. So how do we want to determine the codes? Better to use a table. So if the value drops between the range of a certain code word, so we can assign the code word to that specific sample. Okay, so this is what we call as the PCM code word. PCM code word, dia dalam binary. Okay, it is in term of binary. Boleh So that's all I want to explain about chapter 4. Additional explanation. Okay, yang mana saya tak terangkan dalam video. So I think that's all for. If you have question you want to ask.
Doktor.
Ya, silakan.
Okay, tadi ni 3 bits, so dia punya quantization range tu dia memang fix 3.5 volt to negative 3.5 volt ke akan berbeza?
Okay, dalam example ini dia antara 3.5 sampai negative 3.5. So it depends. It can be any value. For example, 10 volt until minus 10 volt. Also can, no problem. So this is what we call as the range. Okay, peak to peak range, the peak to peak.
Tapi yang value tu akan diberi.
Kalau dalam soalan ada soalan seperti ini, maknanya dia punya value dia perlu berikan. Okay, ini sama seperti dalam example yang ini sekejap ni. Okay, dia seperti example 6.4 ini yang mana diberikan nilai peak to peak minus 6 until 6 volt. So between 6 to minus 6 we are using 14 bits. Ni besar dia punya bit dia ada 14. So 2 kuasa 14 ada 16,384 levels. Okay, we have 16,384 levels. How much is the resolution? So peak to peak divide with the dynamic range, so we get the resolutions. So if you ask me, the value depends. Bergantung kepada nilai yang diberikan. Berapakah nilai peak to peak untuk quantization tersebut?
Thank you, Dr.
Ada soalan lain nak tanya? So my explanation for today is for slides 36, 37, and also you can refer to this example from Frenzel books, example 6.4b. So so why I explain this one, because this is important for your final exam about PCM, pulse code modulation. Remember that PCM is a type of encoding process. PCM adalah encoding process yang kita gunakan selepas quantization process. So we have a sampling process, sampling process, and then quantization process, and then encoding process. After encoding, we produce the PCM code word. So this is important for you. Boleh So kalau ada soalan boleh tanya. If you don't have questions, we can finish now. 10:27. Ada soalan nak tanya? If you don't have questions, yes.
Yang saya that I was say about the final topic tu, this one lah kan doktor?
Final topic
Yang PCM yang tadi saya ada tanya doktor, what is the important topic? So doktor cakap tadi pulse code modulation, which is this one lah kan? For chapter 4. Alright, okay. That's all from me.
So for final exam, you can refer to my first video about chapter 4. Saya berikan 2 video kalau you lihat. Actually sehingga video yang pertama pun dah cukup untuk final exam. Okay, it's enough.
Doctor, for the confirmation, which is FSK didn't tak masuk kan untuk final. FSK and LSK.
Dah masuk. That
Okay.
one is under digital transmission, broadband transmission, yang mana itu tidak masuk tak masuk dalam final.
Alright. Okay, thank you, Doctor.
Okay, welcome. So boleh So I hope that you try to practice about PCM folded binary so that you can have more understanding about the PCM. Okay. So ada soalan? Tak ada soalan. If you don't have question, I will.
Doktor, saya nak tanya pasal topik yang ni belakang kan ada error function table kan?
Error function table. Ya.
Yang tu macam mana nak refer
Error function table je. Ni. How to refer to error function table?
Yeah.
Okay, how to refer to error function table? It is based on these equations. So first of all, you need to find how much is square root of EB over 2n0. This is for the ASK, coherent ASK. So first of all, you need to find how much is a bit energy over 2n0. So after you find this value, for example, this one is for example berapa tadi 3. Katalah 3.5 for example. Okay, so ERFC 3.5, you can look at ERFC table, the second table. So ini besar sangat so katalah 1.1. Ini besar sangat So katalah 1.1 for example. Okay, for square root of EB over 2n0, katalah you dapat 1.1 for example. So this is belong to ERFC. So actually ERFC in bracket 1.1. So you need to look at the ERFC table. Complementary error function table is the second table. So this is the ERFC. So 1.1 is here. So this is 1.0. Here is this is 1.00. So 1.1 is here. Okay, 1.1 is here. So this is the value. So you get 0.111979. Okay, this is for ERFC 1.1. Okay, so it is actually like this 1.10 sebenarnya 1.10. So the ERFC function is 0.11979. And then this value put inside the equation, masukkan dalam equation, you darabkan dengan 1/2, baru you dapat probability of bit error. So this probability of bit error is the probability that the receiver will produce error. Kebarangkalian receiver akan menghasilkan error. Contoh for example, if you transmit 110 suddenly the receiver interpret this code as 111 111. So from here you see that there are 2 bits error. So this is the error that happens. So probability of bit error is to show how much is the probability that this error will occur. Berapakah kebarangkalian nilai akan berlakunya error. So probability, you see that probability is from 0 until 1. Okay, nilai probability adalah daripada 0 sehingga 1. So dia antara 0 sehingga 1. So berapakah dia punya kebarangkalian berlakunya error. So lagi besar nilai probability of bit error, lagi besar kemungkinan berlakunya error. Am I jawab you punya soalan ke tak?
Jawab. Cuma dekat sini yang doktor assume 0 hingga 1 tu kena ambil dari mana Sebab
Ini
yang ya.
0 1 je. This one lah. So probability. So you are given two tables, satu complementary, satu lagi error table. So this is related sebenarnya. So you can normally we use a one table only is enough. Okay. So kalau you lihat di sini daripada senang error so this is from 0 until 1 so this is kebarangkalian. Kalau you lihat the mathematics of probability. 0 until 1. So 0 means that dia kemungkinan besar ataupun tidak berlaku. If the probability is 1, that means it will happen. Okay, dia akan kebarangkalian berlaku tu dia pasti. So this is between 0 until 1.
So yang lain, value lain tu boleh jarang ditanya lah. Maksudnya biasa dia akan tanya 0 sampai 1 saja.
Biasanya dia antara 0 point something. So the probability is normally from 0 until 1. 0 is it will not happen. 1 is surely will happen. So normally the probability it will happen is between 0 point something. So normally in the final exam questions, kita akan berikan nilai EB and also N0. From there you can find the ERFC parameter, and then you can find the probability of bit error. So normally if you see from the final exam questions that they ask about how much is the probability of bit error. Itu pernah ditanya sebelum inilah. Yang mana you kena gunakan table untuk mencari ERFC function.
Baik doktor, thank you.
Ada soalan lain? Tak ada?
Tak ada doktor. Which is dekat checkbox ada Anwar Khalid bin Anwar bin Abdul Alik, which is dia ada interview for an internship.
Dia ada apa?
Dia cakap macam ni, Doctor, I have an interview for an internship, so I have to go to attendance. Can I get my attendance later?
Okay, no problem, boleh. Okay, boleh. So kalau tak ada soalan, kalau ada boleh tanya, kalau tak ada kita akan pergi kepada attendance lah. Okay. So if you see from here, if you ask me, sekejap. Okay. So kalau you lihat these lecture notes, actually is divided into two main parts. The first one is about what we call as dipanggil sebagai okay. The first one is this is the baseband transmission, which is up to this baseband. So this is up to the baseband. Okay, so up to here before digital modulation. So digital modulation starting from slide number 53 until the end, that one is about ASK, FSK, PSK. Okay, so if you ask me, your final exam is, I can say that up to slide 52, okay, which is regarding the baseband transmission. Okay, and PCM is far before that. PCM jauh sebelum itu, iaitu kalau kita lihat sehingga slide yang ini 45. So if you ask me, slide 45 is enough for the final exam. Okay, up to here. But if you want to get a clear picture about digital modulation, of course, I ask you to read until the end so that you can have more understanding. Okay, so PCM, of course, PCM. Okay, PCM is not yet until line coding. Okay, so PCM we produce a code word. Now the issue is how we want to transmit the code word. We can use a line coding where we change the code word into electrical pulses. Kita dapat code word tadi. Macam mana nak tukar code word itu kepada electrical pulses dalam bentuk voltage? So that one we need to use a line coding, which is this one. Okay, so you see that here, the above part here is the PCM code. So I already make it here is a PCM code word, and we change the code word into electrical pulses menggunakan line coding. So there are a lot of line coding method that we can use. Okay, so if you ask PCM code word, PCM is just a code word. Dia bukan dalam bentuk voltage. Okay, dia baru dalam sebutan binary. The issue is how we want to convert that code word into electrical pulses so that we can transmit. Kita tak boleh hantar 1010, kita perlu hantar dalam sebutan voltage and currents. So how we want to convert it? So it is based on the standards given. Either you want to use a line coding if you want to transmit as a baseband, or if you want to transmit as a broadband transmission, kita boleh pergi kepada digital modulation techniques where we do the modulation with the analog carrier. That one we can transmit as a ASK, FSK, PSK. Nampak So daripada PCM tadi kita ada dua option Adakah kita nak hantar secara baseband menggunakan kabel, biasanya menggunakan kabel where we use a line coding, we convert the code word into electrical pulses using line coding so that we can transmit as a baseband transmission along the cable. Or if you want to transmit wirelessly, we can do digital modulation with analog carrier. So we do digital modulation with the analog carrier using the PCM code word. We modulate with the analog carrier, and then we produce ASK, FSK, or PSK so that we can transmit the signal wirelessly over the air. Itu adalah broadband transmission, yang mana kita hantar menggunakan frekuensi tinggi, radio frequency. So that radio frequency is depending on the carrier frequency that we do the modulation. Okay, that analog carrier. Okay, so itu ada dijelaskan dalam saya punya video, first video and second video. Okay, so kalau tak ada soalan, kita pergi kepada ini kita pergi kepada attendance. Untuk kawan kamu yang ada interview tadi tu, boleh message saya nanti nanti saya akan masukkan nama dia. Tadi siapa nama dia, you ingat lagi tak?
Anwar bin Abdul Alik.
Abdul Alif Okay. So switch on your QR code reader so we can do the attendance. So now is 28. So okay, you can scan. So after you scan your attendance, you can go to another class, or I suggest, since we have a few minutes time, I suggest you to have discussion with your group member about your project so that you boleh siapkan tepat pada masanya. So for those that haven't used the time slot for Q&A, so I suggest you to Okay, choose the time as soon as possible so that saya boleh arrange saya punya masa untuk kamu lah. The reason why I choose the time during study week so that I want to give you more time to prepare for the project. Mungkin ada sebahagian pelajar yang kurang senang kenapa buat waktu study week, mengganggu saya punya study. So I hope I'm not disturbing your study time. I just take 15 minutes only for your time during the study week for the Q&A only. So you perlu ready hanya pada 15 minit tersebut sahaja. Okay. So kalau ada soalan boleh tanya sekarang. Kalau tak ada, please discuss with your group member. We have a few minutes, so please use your time properly.
Thank you, Dr.
Okay, welcome. Ni ada 12 orang. Siapa lagi ni? 11 orang. Banyak siapa?
Doktor,
Ya.
untuk projek tu,
Mhm.
coding yang kita buat dalam MATLAB tu kita perlu terang daripada awal kita buat sampai habis ke?
Banyak kan coding tu?
Dua banyak.
Tak perlu tunjuk semua. You boleh tunjuk yang beberapa kerat yang utama sahaja. You take the main codes only and then you explain. You tak perlu tunjuk every function. Saya tak nak. Itulah maksudnya kita just tunjuk function yang utama apa dia. So I just want to see that you understand about the codes. That's it. Saya tak nak tengok every detail setiap baris tu, tak.
Kira terangkan function yang berkaitan dengan projek yang kita buat je.
Ya.
Okay.
So coding tu panjang, so you ambil beberapa bahagian yang utama, so that you explain, okay, this function is about this and this and this function is about this and this. So ini adalah function-function utamanya. Yang kecil-kecil tu tak payahlah jelaskan very detail, tak perlu. Saya nak tahu yang function utama dia apa.
Okay, terima kasih.
Okay, sama.
Doktor, saya tak dapat nak scan tu. Saya
Nama
punya
siapa?
Ahmad Kamil Haikal.
Ahmad.
Nombor 2.
Ahmad dah. Dah.
Oh dah, okay. Thank you, Doktor. Sorry.
Doktor, tick my Siti Sarah.
Okay, Siti Sarah, okay dah. Yang lain dah?
Okay, thank you, Doktor.
Okay. Who's next?
I'm Osman Adan, 14.
Oh, Osman Adan. Okay. Okay, done. Yang lain mana?
Doktor Anwar bin Abdul Alip dia minta doktor tikkan.
Okay, Anwar bin Abdul Alip. Okay. Siapa lagi?
Hello doctor, my name.
Siapa nama? Syarul Hello? Siapa nama?
Hello doctor, my name is Anwar bin Abdul Alip.
Dah. Anwar dah.
Okay, thank you doctor.
Okay. Ya, yang lain siapa?
Saya.
Siapa?
Doktor Noranisa, doktor.
Muhammad Ainul Nazhan.
Ainul Nazhan. Okay.
Okay, thank you doktor.
Siapa lagi tadi?
Noranisa.
Noranisa. Okay, Noranisa. Okay. Lagi? Dah. Siapa lagi belum? So ada 4 orang tak datang Yang lain ni tak ada. Abrisam, Faris, Syarul Hamizan tak ada Nur Adli Nasir tak ada juga. So kalau tak ada, 3, 2, 1. So I close this one. Okay, kalau tak ada, so kita tutup lah So that's all for today. So I will meet you again during the Q&A session. So I hope that you are ready for the Q&A session during the study week. Only 15 minutes. I just want to ask how you do this project, how your GUI functions, macam mana you buat ini, macam mana you hasilkan dia punya results, adakah result itu tepat ataupun tidak tepat, something like that. So we can have a Q&A session at that time untuk melihat you punya project tersebut. Sebab dalam assessment itu dia ada peruntukan yang mana saya perlu bertanya soalan directly. So I cannot just base on the video. Video is for me to understand first. So I will see your video first, and then we go to the Q&A, so that saya boleh tanya soalan. Okay. So that's all for today and this semester. So see you again later. Okay. So good luck and all the best to you. Okay.
Okay,
Thank you, Doctor.
Thank you, Doctor. Bye bye.
Thank you, Doctor.
Terima kasih, Doktor.